All right, so in this video, we'll be looking at the relationship between a couple of key variables, such as your speed of light, wavelength, and frequency. And so when you're studying light, photons, electromagnetic waves, this formula is everywhere in AP chemistry, general chemistry, even physics. So it's very important that we understand and have a solid grasp of the relationship between these different concepts. And so the core formula that connects these three is going to be C is equal to lambda nu. And so in this formula, C, that is going to be your speed of light. Speed of light we denote with the letter C. And this is going to be equal to 3 times 10 to the 8th meters per second. And this is a constant, right? Like if you remember in the last video, we were looking at Planck's constant. That value stays the same. So this is a constant value. Our lambda here, lambda, the Greek letter lambda, is used to represent the value of the wavelength. Wavelength. And our wavelength is going to be in units of meters. And that's important. And what you'll see is often we'll be given our wavelength in units of nanometers when we're dealing with problems because these waves are very small. So we'll often be given units in terms of nanometers instead of meters. But you should key to remember the wavelength needs to be in meters if we want to use this formula. In practice, the wavelength is given in nanometers, and so we always have to convert. And so if we want to convert 1 nanometer into meters, well, 1 nanometer is 1 times 10 to the negative 9 meters. So if we're given our wavelength in nanometers, you're simply going to have to multiply by 10 to the negative 9 before using the formula. Okay. And well, we're talking about wavelength a lot, but it's not exactly clear what that is. So let me just quickly demonstrate what the wavelength is. Well, let's say that we have a wave. And so the wave, we can see, right, oscillates up and down repeatedly in this fashion. And so effectively, a couple parts of the wave that we need to identify are going to be, first, these peaks, right? These peaks, they are called the crests. This is one crest, here's another crest. This is the crest. These are the crests of the wave. And well, on the bottom, these also have a name, right? These are your troughs. 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 So we have our crests and our troughs. And so, what is the wavelength? Well, the wavelength is going to be the distance between one crest to another, or whether from one trough to the next trough. This value, this distance, that is going to be our lambda. Our lambda. This is our wavelength. So that is what we're talking about when we say wavelengths. All right. So we have our wavelength. That's going to need to be in units of meters. It'll often be given to us in nanometers because, dealing with very small waves. But remember to always convert that to meters. And well, finally, we have our nu. Nu, or we can also denote this with the letter F, which we talked about in the last video. This is basically going to be used to denote our frequency. Frequency. And frequency, we're going to be using the units of hertz to measure. Hertz, again, this is just cycles per second, and so the units of second to the negative 1, 1 over second, these are all equivalent. And so this is just going to be the units that we'll be using to denote our frequency. Well, now that we kind of see what each of these letters represents and we see this foundational core formula, well, we can actually use this to find a lot of other things. And by other things, I mean we can manipulate this or algebraically manipulate it to isolate for certain variables to solve for when we have others. Well, we see that the speed of light is wavelength times frequency. So that means we can find, say, if we're given our frequency, we can find our wavelength. Our wavelength is going to be equal to simply, if we isolate for wavelength, we just divide both sides by frequency, and we can see that the wavelength is C divided by nu. So our wavelength is going to be our speed of light divided by our frequency. Similarly, let's say we have our wavelength and we want to find our frequency. Well, the frequency nu is going to be equal to speed of light divided by lambda, our wavelength. Again, this is just simple algebraic manipulation of this basic formula here. And we can do this because, well, our speed of light, that value is always going to be constant. We have that constant 3 times 10 to the 8th meters per second. And so it's only variations in our wavelength and frequency here that are going to be making a difference. And from this, we can see an important relationship or an important relationship between these two variables. This equation is showing us that wavelength and frequency are inversely related, right? We can see that if the wavelength goes up, the frequency is going to go down, and vice versa, right? If we increase the value of the denominator of a fraction, well, that decreases the overall value of the fraction. Let's say we had 1 over 10. Well, that is 0.1. 1 over 100, if we increase that value of the denominator, that's 0.01. You can see that by increasing the value of the denominator, we decrease the value of the overall fraction. And so in this way, we see this inverse relationship. We establish an inverse relationship between wavelength and frequency. And so, well, what does this mean? Well, we can see again, because the speed of light is constant, long wavelengths have low frequencies and short wavelengths have high frequencies. So, for example, red light, well, that is a longer wavelength and has a lower frequency. Blue or violet light has shorter wavelengths, very small wavelengths, and because of that, they have a much higher frequency. Another thing to keep in mind is, if you remember from the last video, we saw how we could find the energy of a photon if we were given its frequency, right? So we can see E equals h nu, where here E is the energy of our photon. H, just as a quick reminder, that is going to be our Planck's constant. Planck's constant, which is going to be equal to 6.626 times 10 to the negative 34 joules per second. And again, we know this nu again still represents frequency. So, okay, well, we can find the energy of a photon given its frequency. That makes sense. But what if we're given the wavelength? Is there a way we can find the energy in that case? Well, the answer is yes, right? We can see just from what we've established here that given our wavelength, we are able to find the frequency, right? And so all we have to do is simply substitute this for the value of nu. Instead of nu, we would substitute this expression as their equivalent, right? So, well, then that means if we want to find the energy of a photon given the wavelength, or if we want to find energy given the wavelength, that's simply going to be E equals Planck's constant, h, and instead of nu, we would simply have c over lambda. So speed of light over wavelength. And so in this way, we are able to find the energy if we were given the wavelength. And so basically in this way, we are able to relate these different core concepts to isolate and solve for different values, right? So that's an important thing we can understand. And now let's just look at some problems to make this clearer. So what is the frequency of light with a wavelength of 500 nanometers? Well, let's start with our original formula of c equals lambda nu. Here we're trying to find our frequency, or nu, so we can isolate for that. Be getting c over lambda gives us our frequency. We know that our speed of light is 3 times 10 to the 8th meters per second, which we divide by our frequency of 500 nanometers. And well, if you remember, we talked about the fact that we have to go from nanometers to meters if we want to use our wavelength. Our wavelength has to be units of meters. And so we can do that, like we said, by simply taking taking the value in nanometers and multiplying by 10 to the negative 9. And this gives you an answer in units of meters, which if we want to keep in scientific notation, we can also just do as 5 times 10 to the negative 7. So let's do 5 times 10 to the negative 7 meters. And this then will give us our answer as to be 6 times 10 to the 14. We can see meters cancels out, giving us 1 over seconds, which we know is the same thing as hertz. So let's just write it in units of hertz. So this is going to be the frequency of our light with wavelength of 500 nanometers. Right now, a radio station transmits at a frequency of 95.5 megahertz. What is the wavelength of the wave? We'll see that we're given our frequency in units of megahertz. So first, we're going to have to convert from megahertz to regular hertz. And so we know this prefix of mega, like we know that, if we're trying to go from kilograms to grams, we know that there's 1,000 grams in a kilogram. So similarly, we can convert from megahertz to hertz. And so if we have 95.5 megahertz, well, that's just the same as this is equal to 95.5 times 10 to the 6th, or 9.55, if we want to write it in scientific notation, times 10 to the 7th hertz. So this is going to be the frequency value that we'll be using. And while we know that C is lambda nu, here we're trying to find the wavelength. So lambda is C divided by nu. So 3 times 10 to the 8th meters per second divided by 9.55 times 10 to the 7th hertz, which we know again to be seconds to the negative 1, if you want to write it that way. Comes to the negative 1. This is going to cancel out our units of seconds, giving us an approximate answer of 3.14 meters. Right, now we're told that a light wave has a wavelength of 600 nanometers, and we have to find the energy of one photon of this light. Well, first, again, we're told the units of wavelength in nanometers, and we know that we have to always be dealing with meters, and so let's just start off by making that conversion. So we know that we have 600 nanometers, which we want to convert to units of meters. And we already talked about this, right? Before, this is just 600 times 10 to the negative 9. That's going to give us our answer in meters. And simply with scientific notation, that's 6 times 10 to the negative 7. So we'll use this value for our wavelength. But first, we need to find our frequency. And well, why? Because we know that this is our formula. Energy equals H times nu. And so there are two ways that we can approach this problem. One is we can plug it into this formula, in which case we would need to use this wavelength to find our frequency, which again we would do by getting our nu equals C over lambda. And so if you remember, we could also simply approach this problem by substituting this in, by doing this. So either is, acceptable. Either way is acceptable. So, in this case, let's do this, right? We can derive this formula, so let's use this one. So we can see that our energy is going to be Planck's constant times the speed of light divided by our wavelength, which is going to be 6.626 times 10 to the negative 34 times our speed of light, 3 times 10 to the 8th. And now we divide by our wavelength, 6 times 10 to the negative 7. And this is going to give us an answer. This is going to give us our answer of 3.31 times 10 to the negative 19 joules. All right, so let's look at one more. So here, we're told that a photon has energy of 2 times 10 to the negative 19 joules, and we need to now find its frequency and wavelength. So we're starting from energy, and we're trying to get frequency and wavelength. So here, let's first use this formula. Our energy is equal to Planck's constant times nu, and solve for our frequency here. So then by isolating for nu, let's do it here. That's just going to be our energy divided by Planck's constant, or 2 times 10 to the negative 19, divided by Planck's constant, which is 6.626 times 10 to the negative 34. And this is going to give us an answer of 3.02 times 10 to the 14 hertz. So this is our frequency. And well, now we can simply find, so we already have our frequency. This is, part 1. We got this answer. But now we can find our wavelength. We have our frequency, so we know using this formula, isolating for wavelength, C over nu, we can find our wavelength. So this is just 3 times 10 to the 8th, that's our speed of light, divided by the frequency that we just found, right, which is 3.02 times 10 to the 14. And this is then going to give us a value of 9.93 times 10 to the negative 7 meters. And then if we want to convert this to nanometers, which is, just a general convenience, for convenience sake, that's just 993 nanometers. So, and it's kind of got cut off a little bit. Just write it down here. 993 nanometers. And so then this is going to be our wavelength, and this is going to be our frequency. So that brings us to the end of this video. Hopefully you found it useful. Again, here, this is just simple algebraic manipulation. There's just a couple of formulas that you need to memorize, and the rest of them, it's a lot easier to just derive given the few that you know. And so in any case, if you found this helpful, please show your support by, liking, subscribing, and, leave a comment for what you want to see next. And I'll see you guys in the next video.